Okay, this video is going to cover the pulley. And the pulley is the third simple machine that we would have covered by now. So the first was the lever, then the wheel and axle, and now the pulley. And the pulley essentially is a lever consisting of a wheel with a groove in its rim that is used to change the direction and magnitude of a force exerted by a rope or cable. So let's go through what that means shortly. But first, I just want to give you a little bit of history on the pulley. So Archimedes was a very famous mathematician, engineer, an inventor, and he's credited with the discovery of the pulley. And I think one of his most known pulley systems was what we call the claw of Archimedes. And the claw of Archimedes was able to use a compound pulley system in order to actually lift boats out of the water and capsize them during wartime. And the amount of effort force that was put into these war machines was very minimal compared to the amount of force that it could actually lift. So there are two different kinds of pulleys. The first is a fixed pulley and the second is a movable pulley. So a fixed pulley can be considered a first-class lever, and it will always have an IMA equal to 1. So there's essentially no mechanical advantage associated with a fixed pulley. So if we take a look at what a fixed pulley looks like, so a fixed pulley is essentially attached to the ceiling or some type of a device, and it doesn't move when you pull on the rope. So essentially what you're doing is just throwing a rope, right, over this pulley, and the effort force that you're pulling on, the effort force is applied to one end, and the resistance force that you're trying to lift is applied to the other end. So what kind of lever system does this look like if the fulcrum is in the middle, right? So this is what we would call a first-class lever, okay? Now, the pulley is a symmetrical circle, right? So the distance from here to here and here to here is going to be equal. So if the diameter of the pulley is, let's say, 2 feet, then this would be 1 foot and this would be 1 foot, right? And the IMA, if we say is dE over dr, would essentially be 1 over 1, and the IMA would be equal to 1, right? Because remember, from the fulcrum to the, let's see, this is the FR. From the fulcrum to the effort force would be your dE, and then the fulcrum to the resistance force would be your dr. Okay. Now a movable pulley will always have an IMA of 2. Okay. So this is set up a little bit differently. So part of it is going to be attached to some type of a fixed device. And we are going to have a rope that's going to go around the pulley system, and we're going to be pulling on it at one end, okay? Now, the resistance force is going to be right down the middle, okay? It's going to be attached to the center of the pulley, and this is what we would call our FR. So in this particular case, this is going to be what we call a second-class lever, right? Because the FR is down the middle, and the FE and the fulcrum are on opposite ends, so that would be a second-class lever. Now, if you remember on a second-class lever, if this is our FE, right, then the distance from the fulcrum all the way to the effort force is going to be our dE. And from the fulcrum to the resistance force here will be our dr, right? So you could see that the dE will always be twice as long as the dr, right? So if the pulley has a 2-foot diameter, right? So from here to here is 2 feet. Halfway is going to be 1 foot. So your IMA, which is dE over dr, will always be 2. Okay, so when we talk about pulleys in combination, the IMA is still going to be the dE over the dr, but a shortcut is going to be the number of strands opposing the force load, right? So if this is the force load here, right? Here's our FE that we're pulling on. If we just count, this is FE. If we just count the number of opposing strands, so here's 1, here's 2, here's 3, here's 4, then our IMA will be 4. Okay, we don't count this strand because it's not an opposing strand of the force load. Okay, so let's take a look at some examples. Okay, we have 2 strands here opposing the force load, so our IMA would be 2. 3 strands opposing, so we have an IMA of 3. Here, we will count the effort force strand because it is an opposing strand, so we would have an IMA of 4. Okay, so what is the IMA of the pulley system on the right? If here's our FR, how many strands are going to be opposing? It's going to be 2, right? So the IMA is going to be 2. Okay, now when we talk about, we've been talking about simple machines, but in reality, machines that exist in the real world are going to be compound machines, right? So like automobiles and lawnmowers, bicycles, those are all going to be compound machines, which essentially means it consists of more than one simple machine. So when we talk about more than one simple machine, in order to get the IMA, we have to multiply the IMAs of the different simple machines that are involved in the compound machine, right? So in this particular case, we have 2 different simple machines. We have a pulley system and we have a lever system, right? So we just said, how do we get the IMA of a lever? Okay, so here's the FR, okay? How many strands do we have opposing on the pulley? 2, right? So the IMA is going to be 2 for the pulley. Now the IMA for the lever, is going to be DE over DR, right? Okay, so let's look at where's our DE and where's our DR. Remember, we always measure from the fulcrum. From the fulcrum to the resistance force will be our DR. From the fulcrum to our effort force will be our DE. And it gives us those values, right? So the DR is 4 and the DE is 12. So that would essentially be 12 over 4, right? Which is 3. So the IMA of this lever is 3. So if we multiply 2 times 3, the IMA of the compound machine is going to be 6. So you can see how we can increase the mechanical advantage of a machine simply by combining simple machines to make a compound machine. Okay, so pulleys in combination. What we just recently talked about was pulleys with a single rope, but we can also have pulleys with separate ropes or cables, right? So if we look at this example, we see 1 rope here, 2 ropes here, and 3 ropes here. So if a pulley in combination has a more than 1 rope, then we have to consider each pulley as a different simple machine. So this would be 1 simple machine, 2, and then 3. So we have to get the IMA of each one, and then we multiply it, right? So the IMA of this one is 2, right? 2 opposing strands. IMA of this one's 2, again, 2 opposing strands, and 2 opposing strands. So it would essentially be 2 times 2 times 2, 2 times 2 times 2, which would be 8. Okay, so now we need to talk about AMA. And AMA is essentially going to be FR over FE, right? So FE is the effort force that we're applying, and FR is the resistance force that we're trying to overcome, right? So in this case, it would essentially be 800 divided by 230 would give you your AMA. Okay, 3.48. And then we also need to look at efficiency of the system. Once we know our IMA, so the IMA, remember, count the opposing strands, so that's 4 to the IMA. And we know our AMA, 3.48, so we can simply divide the 2, and we get our efficiency of 87% for this pulley system. Okay, one more thing to talk about is that angles do matter when we're talking about the effort force that we're applying on a pulley system, right? So if we apply an effort force here completely parallel to the resistance force, right? And if we compare that to if we were to actually angle the effort force compared to the resistance force, it is actually going to be harder for you to pull on. You're going to have to apply more effort force in order to lift this resistance force than if you were to simply just lift it completely parallel to the resistance force. Okay, so that's the concept that you need to understand, is that when you angle out your effort force, it's going to be harder to lift the resistance force. Okay, so essentially what's going to happen, because you've increased the FE, right, your mechanical advantage of your system is going to go down. Okay, and that's it for pulleys.